Hello everyone, welcome to our final project presentation. We are Team 18 and these are our team members. In our final project, our work is based on this reference paper, Revisiting MAE Pre-Training for 3D Medical Image Segmentation, which is published on CVPR 2025. For this paper, the core achievement is demonstrating that the well-configured MAE pre-training model, S3D, can consistently and significantly surpass the acknowledged strongest NNU net baseline. First, let's talk about the motivation and the challenges this paper wants to overcome. While self-supervised learning has been successful in 2D, 3D medical images presents unique characteristics and has lots of challenges. Let's quickly contrast the essential differences between 2D and 3D medical imaging. First, structure and resolution. 3D imaging is a volumetric cube with strong depth continuity across slices. Resolution is massive, up to 160 cube to 512 cube voxels, posing extreme computational demands. Second, visual cues. Unlike the strong textures in 2D, medical images feature low contrast and subtle boundaries. Third, imbalance and cost. Class imbalance is severe, with lesions sometimes less than 1% of the volume. Furthermore, annotation is extremely expensive. And last, model requirements. These factors mandate the use of a 3D CNN with a strong inductive bias for 3D medical imaging. Why emphasize the 3D CNN? Because transformers underperform in 3D medical imaging. There are two reasons. The first is computation and memory. The self-attention calculation is quadratic. In huge 3D volumes, the patch count explodes, immediately cause GPU memory explosion and making training infeasible. The second one is structural limit. Transformers lack the strong inductive bias crucial for an atomical continuity, struggling to achieve the required voxel level precision. The conclusion is evident. CNN's special unit variants consistently outperform transformers in 3D segmentation. This is why our paper chose a 3D CNN backbone as the foundation of optimizing MAE. We just concluded that we need a CNN architecture for 3D medical imaging. Now, let's look at how to apply the powerful self-supervised learning paradigm. That's Maxed Autoencoder, MAE to CNNs. MAE is a framework where the model learns by reconstructing heavily maxed input. Its core concept is highly asymmetric. The first is masking mechanism. We randomly mask around 75% of the image's patches. And the second one is encoder. The encoder then processes only the remaining 25% visible patches. This sparse input forces the model to infer global structure rather than simply memorizing details. And the final one is decoder. A lightweight decoder handles the reconstruction of the masked patches. This design is incredibly strong for self-supervised pre-training and has achieved great success with VIT in natural images. This slide visually demonstrates how MAE works. On the left, you see the about 75% maxed input, and on the right, the reconstructed output by the model. You can observe the model's ability to restore a complete, semantically coherent imaging based only on the sparse input. Our challenge now is to bring this exact principle into the world of 3D CNNs. However, applying MAE directly to CNNs fails. This is because CNNs are inherently designed for dense inputs, leading to several issues. Like we have spatial continuity destruction. The high-ratio random maxing destroys the spatial continuity expected by CNNs, rendering local convolutions meaningless. And feature collapse. The feature maps quickly collapse under a high max ratio, failing to extract useful information. We also have UNet challenges and sparse handling. Even the crucial skip connection in the UNet architecture break under random maxing, and the simply cut CNNs cannot natively handle sparse inputs, unlike the transformers handled the max tokens. Therefore, a fundamental adaptation of the CNN architecture is necessary. So, let's talk about the innovation of the model of this paper, S3D. S3D addressed the sparse input problem for CNNs, and S3D innovations aims to make the CNN encoder max aware, just like Vision Transformer MAE. The first step is sparse convolution. The key here is not treating max voxels as zeros. Instead, S3D models them as absent. Convolution is computed only on visible voxels, which prevents feature collapse under a high masking ratio. And the second step is sparse normalization, also called sparse batch norm. Traditional batch norm expects dense statistic, and S3D introduces sparse norm, which computes mean or variance only from visible voxels, effectively avoiding unstable activation when 75% of voxels are missing. These steps enable the CNN encoder to become max aware. With the sparse encoder in place, the next step is reconstruction, the focus of S3D innovation 2, reconstructing dense volumes. The first step is max token densification. When CNNs cannot insert a trainable max token like Transformer MAE, S3D introduces dense placeholder for the missing voxels. This ensures the decoder receives spatially aligned feature maps. And the second step is densification convolution. Subsequently, a 3x3x3 convolution layer is applied. This local convolution converts the sparse encoder outputs into a dense 3D feature map, filling the gaps so the decoder can now operate like a normal UNet decoder. The third innovation of S3D focuses on architecture choice and parameter optimization. The first is residual encoder. S3D chose to use the strong CNN backbone from an UNet. The residual encoder, UNet, it is a natural fit of volumetric segmentation and ensures stable gradients under space input. And for the optimal masking ratio, through extensive abstraction, the team found that a 75% masking ratio delivered the highest downstream performance. Lower ratios or higher were suboptimal. Through these three levels of innovation, S3D became the first MAE that works well on 3D CNNs. In this chart summarizes S3D's final outcome. S3D consistently improves performance by nearly 3 disk points. It surpasses all existing SSLO method and is the first to prove the MAE paradigm can consistently beat the strongest NNU baseline. And why S3D outperforms 3D MAE? S3D's advantage lies in its choice of architecture. The key reasons S3D outperforms VIT-based MAE is anatomical match and performance stability. The CNN inductive bias perfectly matches the anatomical continuity of medical imaging, and S3D handles full resolution volumes, requires less computation, and is more stable during fine-tuning, resulting in stronger dice performance. We applied S3D to our project, the 3D segmentation of hard CT. The hurdles of our test is that handling high spatial complexity, small target, and limited labels. The help of S3D is that S3D provides a strong global anatomical representation, handles 3D continuity, and reduces the need for expensive labels via SSL, aiming for better downstream performance. We are now applying the S3D methodology to our practical challenge, the AI Cup 2025 Hard CT segmentation task. This is a classic 3D volumetric segmentation problem. Taking hard CT data as input, we must accurately segment four classes: the background, heart muscle, the erratic math, and the critical classification points. The difficulty is twofold. First, the classification class is a textbook example of a long-tail class. It occupies a minuscule volume fraction, yet clinical accuracy depends on its precise detection. Second, we are testing a strategy optimized for MRI at 3D on a radically different modality, CT. The visualization on the right shows the high-resolution nature of the data, illustrating the complex 3D relationships between the large muscle volume and the tiny challenge target structures. To address the high complexity and severe class imbalance, our final method employed a comprehensive three-stage pipeline: pre-training, fine-tuning, and post-processing. First, in the pre-training phase, we utilize the NNSSL S3D method with a residual encoder, NNUNet backbone. This step involved training on a large volume of unlabeled CT data. We leverage S3D's innovations, the sparse convolutions and sparse normalization, to ensure the 3D CNN could robustly learn a dense feature map representation of the heart's anatomy explicitly modeling the long-range spatial continuity crucial for 3D volumes. Second, the fine-tuning phase used the full AI-Cup training set with ground truth labels. Here, we transfer the pre-training weight from the S3D encoder to initialize our NNUNet model. The model was then fine-tuned using standard volumetric loss functions to specifically localize four target classes. Finally, the post-processing phase, which was our critical practical contribution, targeted the long-tail issue. We employed a 3x3x3 kernel to perform connected component analysis and erase isolated predicate labels. This step acts as a powerful spatial filter, explicitly removing isolated single voxel predictions or small spurious clusters, which are highly likely to be false positives for the tiny classification class. These final refinements significantly enhance the clinical plausibility and metric score. Let's examine our results. The metric used was the average of DICE and IOU. Our project was highly competitive. Our final best score was 0.79678, securing us rank 56 out of 568, successfully placing us in the top 10%. However, we observed a critical finding. The pre-trained S3D model scored 0.79042, which was actually a decrease compared to the stretch-trained NNUNet baseline. This highlights the extreme challenge of cross-modality domain shift. The SOTA features learned on MRI did not transfer effectively to the CT domain. Ultimately, our best goal was achieved by relying on robust NNUNet baseline combined with our text-specific post-processing technique. Now, let's visually confirm our results. The images demonstrate the final 3D segmentation mask from our best model. Look at patients 52 and 61. First, we successfully delineate the large heart muscle volume, confirming the effectiveness of the CNN inductive bias. Second, and critically, observe the internal classification points. Achieving this required the fine-tuned cleaning effect of our post-processing kernel to remove noise. This visualization confirmed our final engineer pipeline delivered a high quality. And for the future work, we outline 3 key areas for this. The first one is scaling. Investigate the impact of pre-training epochs and find the optimal training duration. And we need to find out the input. Perform an extensive page size analysis to better capture both global and local structure. And the last one is data robustness. Test histogram equalization to understand if our SSL is robust enough to handle variation in image contrast. Thanks for listening.